All right. Today, what we're going to do is look at the three definitions of an acid and base. Okay, so it's going to start with somebody named Arrhenius. Oh, did I go too far? Oh, thank God I did. There we go. That's where I want to start. So there's going to be three different ways to define what an acid and base are. And there will be some substances that will be able to fit all three definitions of acid and base. There will be some definitions that will fit only two and some that fit only one. What will determine if something is an acid or base will depend on which definition you are using. So I want to make sure that we take this topic nice and easy, make sure everyone understands each definition and how to apply it. Okay, so the first one we're going to start with is the Arrhenius definition of an acid and base. He was a Swedish chemist, and he was born in 1859, lived to 1927. Doesn't really matter, but just to give you a framework of the time period that we're looking at. He understood aqueous solutions of acids and bases conduct electric currents. Okay, so first thing that we're going to point out here is that he's looking at them from the standpoint of aqueous solutions. The other two definitions are not going to depend on acids and bases being aqueous solutions, but this is criteria number one for, it would help if I could write properly. Criteria number one for this definition. Oh, why does it always do that? Sorry, I'm just seeing. Okay. Right. Okay. Just checking to make sure I got attendance correct. For some reason, every time I swipe my iPad to go to take attendance out of the Keynote app, it exits the Keynote app on my computer, but whatever. All right. So again, first thing we're doing is we're defining both an acid and a base as being an aqueous solution. So this is, again, criteria number one. And as I said, the other two definitions don't have this as a criteria, so they don't have to be aqueous solutions. But for Arrhenius to apply to acids and bases, it has to be an aqueous solution. Now, criteria number two is produce ions. And in case you're not sure what criteria is, let's say requirement. Same thing. So requirement number one is that they are aqueous solutions. Requirement number two, they produce ions in solution. Now, depending on if it's an acid or a base, they're going to produce different ions, and that will be requirement number three. So an Arrhenius acid is defined as a chemical compound that increases the concentration of hydrogen ions in aqueous solution. Okay, so here we've got criteria or rule number one, requirement number one, aqueous solution, and rule number two or requirement number two to increase concentration of ions. And rule number three for an acid is that it increases hydrogen ions. Okay, 1, 2, 3. The acid ionizes in solution and increases the number of hydrogen ions present. And an Arrhenius base is a substance that increases the concentration of hydroxide ions in aqueous solution. So again, we've got hydroxide ions, aqueous solution, aqueous number one, ions number two, and hydroxide number three. Now I want to point out something here. Based on these two definitions, you can conclude that one substance cannot be both an acid and a base at the same time. Okay, you're either going to produce hydrogen ions, or so you're either going to increase, that's a big difference. You're either going to increase the concentration of hydrogen or you're going to increase the concentration of hydroxide. You cannot do both in a single reaction or in a single chemical equation. So when it comes to identifying Arrhenius acid or base, that's exactly it. Or you cannot have both an Arrhenius acid and an Arrhenius base in one equation. Okay, and I'll go through some examples to demonstrate that. Okay, with the other two definitions, that's Bronsted-Lowry and Lewis, the same Lewis that you use to draw Lewis structures for, same guy. You will have both an acid and a base in every chemical reaction because it's based on a transfer of something. So that's different. So the first thing that stands out about Arrhenius is that in any chemical equation, you will be able to identify an Arrhenius acid or an Arrhenius base. For the other two definitions, you're going to be able to identify an acid and a base because, again, the other two definitions are based on transferring something. Some bases are what we call ionic hydroxides, which means that it is usually a metal that is paired with the hydroxide ion. And when you add that compound to water, it dissociates, which is not the same as ionizes. Okay, I want to make that distinction again. There's a difference between ionization and dissociation. Dissociation means that there are already ions present and they just separate when you put it in water. Ionization is when you're literally creating ions where there were no ions before. There is a big distinction between the two. So ionic hydroxides are going to dissociate in solution and release hydroxide, therefore increasing the concentration of hydroxide. Oh, excuse me. Other bases, actually, before I do that, I have to go all the way back. Okay, so I want to do an example of this to show you first. KOH, potassium hydroxide, when you put it in water, you're going to get potassium ions, which are aqueous, and you're going to get hydroxide ions, which are aqueous. This is an example of dissociation. Okay, that's one type of base. Now, you can see and here's the other thing that might be confusing. When you're going to identify an acid and or a base, depending on the definition, and don't worry because I know we didn't have chem yesterday. I'm going to spend the 2 periods next week also talking about the same topic because it requires a lot of practice, I think. When you're going to apply an acid-base definition, you actually have to look at the product side to see what had happened, right? When people say like, what had happened? You have to look at the product side to figure out what had happened between the reactants and the product. So in this example, I look at the product side and I say, okay, what is going on in this equation? I've got potassium hydroxide on the left as a solid. I've got water here. Even if I don't have that present, you don't need that as a requirement because guess what? I can look at AQ and be like, it must be dissolved in water because it's aqueous. So what I'm looking at here is we're increasing the concentration of hydroxide ions and it is in an aqueous solution. So ding, Arrhenius base. Okay, you can use abbreviations because you're going to be labeling a whole lot of things. It's Arrhenius base, it's aqueous, and it increases hydroxide concentrations. Okay, another way to increase hydroxide concentration is for a substance to react with water to remove a hydrogen ion from water, which thereby leaves hydroxide in solution. And a good example of this is ammonia. Ammonia is a gas. When you mix it with water, ammonia is an extremely polar compound. If you remember from our Lewis structures, just in case you don't, I'll do it up here because it's good to review. When you draw a Lewis structure, you add up all of the available valence electrons in the bond. So if you consult your periodic table, nitrogen has 5 valence electrons. Each hydrogen has 1 valence electron for a total of 3. You have 8 electrons available for your structure. You put the most electronegative element in the middle, and then I'm just going to stack my hydrogens around the outside. I'm going to use a straight line to represent a covalent bond. Each covalent bond represents an electron pair. So when I draw them, I'm counting 2, 4, 6. I have 2 electrons left. Then I have to fulfill the octet rule, which says that every atom has a full octet of electrons in its outer shell, unless your exceptions like hydrogen or boron, aluminum, things like that. But almost everything else has a full octet in its outer shell. So there is the Lewis structure for nitrogens. Now, going all the way back to chapter 6 on our topic of bonding. In covalent bonds, especially polar covalent bonds, like in ammonia, you have what are called dipoles. Now, a dipole is where you have electrons that are going to lean more towards the more electronegative element in the covalent bond. And you draw dipoles by pointing an arrow towards the more electronegative element with a little tiny plus sign tail at the other end. So this dipole is showing you that the electrons that are being shared between nitrogen and hydrogen like nitrogen more because it is a more electronegative element. Now, if I do that for all 3 hydrogens, you see that all 3 of my dipoles are pointing in the same direction. The geometry of this is trigonal pyramidal, or I like to refer to it as chicken foot, because it looks like a chicken foot where you have the nitrogen. That one kind of comes out. Oops, that's a hydrogen, sorry. And then you've got one that goes in the background like that. So it's a 3-dimensional kind of a pyramid shape with each hydrogen at the base of the pyramid. The nitrogen is at the tip of the pyramid, and at the tippy top, right hovering above the nitrogen, is its lone pair. If you remember valence shell electron pair repulsion or Vesper theory, this is what tells us that that lone electron pair takes up just as much space as each of these hydrogen atoms because of electron pair repulsion. Okay, so that's what determines the shape of a molecule. So the chicken foot or trigonal pyramidal is the shape. Now, that's a quick review of previous topics. Back to the task at hand, we have ammonia here is a highly polar molecule, as we saw from our Lewis structure. So it is basically going to steal a hydrogen ion away from water, and it's going to form an ammonium ion, and what you're left with is hydroxide. So it's not creating hydroxide ions directly by dissociation, but it is creating a higher concentration of hydroxide by taking a hydrogen ion away from water, which naturally produces hydroxide. So again, if we're applying Arrhenius definition, we have an aqueous solution, check. Hydroxide ions, check. It is an Arrhenius base. Okay, hope that makes sense. All right, now the acids described by Arrhenius are molecular compounds with ionizable hydrogen atoms. That means that their water solutions are called aqueous acids. All pure aqueous acids are electrolytes because they are ionizable. And remember, the only thing that you need to have electrolytes are ions that can move around. The acid molecules are polar enough so that one or more hydrogen ions are attracted by water. So negatively charged anions are left behind. Now, the hydrogen ion in the aqueous solution doesn't actually exist as a single hydrogen ion because this is extremely unstable. It's literally just a proton, right? So you can't just have single protons flying around in solution. They're going to immediately react with a water molecule to produce hydronium. So hydronium is a more accurate representation of what's actually in solution. Let's look at an example like nitric acid. Again, this is an oxyacid. In order to name an oxyacid, just to review what I talked about last week, you use the shortcut adic. Adic. Oop. Okay, and of course my Bluetooth just crashes. That's awesome. Try again. Us or itis adic. I think that's the way I usually say it. Itis adic or adic itis. So if the polyatomic ion ends with ate, the acid ends with ic. So this is nitrate, which means this becomes nitric acid. Okay, just to review that. So when you put HNO3 with water, this is what's called the acidic hydrogen that is going to combine with water to form hydronium in this equation. So you've got HNO3 liquid plus water liquid, and then this hydrogen is going to bond with water, and you're going to leave the nitrate ion behind and form hydronium. So Arrhenius, aqueous, check. Hydronium or hydrogen, check. It is an Arrhenius acid. So again, you have to look at the product side to see what had happened in order to apply your definitions of acids and bases. HCl is going to ionize in a similar way. Now, I want to point out, I'm using the term ionize now, not dissociate, ionize, because this is ionization. The hydrogen here is not an ion. That's why I say, when I tell you last week and review this week about using this shortcut, that's not how these acids actually form. The way they actually form is by having a non-metal oxide react with water to form the acid. Okay, so this is all covalent, which means this is covalent, which means there are no ions. But you're producing ions on this side, so therefore ionization, not dissociation. HCl, similar thing. HCl gas, this is covalent, no ions. And then over here, ions, that's ionization. So again, aqueous, check, hydrogen, check, Arrhenius acid. Okay, this is just a 3D ball model of the same thing. Okay, and then you notice you've got H3O. Oops, that's not 3. H3O, which is hydronium, and nitrate. Okay, now getting to strength. There's going to be a couple of ways, and I don't think Gert's here today, but she was asking me yesterday, I think, for help. And she said, how do I know if it's strong or not? Okay, well, here's where I explain where it's strong or not. A strong acid ionizes completely in aqueous solution because remember, the more ions that you have, the strength of the electrolyte or the acid increases. Okay, so electrolytes and acids and bases work the same way. I think I mentioned that last week as well. If you have acids and bases that ionize more, they're going to be stronger electrolytes. This is why all strong acids and all strong bases are also strong electrolytes. Examples of strong acids, we have perchloric acid, hydrochloric acid, and nitric acid. Again, remember a binary acid, you have the prefix hydro, and then the root of the non-metal, ic acid. Now, the strength of the acid is going to depend on the polarity of the bond between the hydrogen and the rest of the compounds, how easily it breaks. If it doesn't break very easily, it's going to be a weak acid. And a really good example of that is if you look at the the halogens, okay? HCl, HBr, and HI are all strong acids. However, hydrofluoric acid is weak. And you might think, why is it weak? Well, what do I always say about fluorine? Okay, I always try to give you like general rules of thumb and like certain like red flag keywords or clues that will trigger something in your memory. And hopefully when I talk about like, what's so special about water? The first thing in your head is polarity. And I say, what's so special about fluorine? I want you to think electronegativity. It is the most electronegative element on the periodic table. So the bond between hydrogen and fluorine is going to be really, really strong, which means you're not going to be able to ionize it very well because hydrogen and fluorine like each other really like just so much because fluorine is the most electronegative element. So hydrofluoric acid is the weakest. When you go down the group of the halogens, your electronegativity is going to decrease, which means that the strength of your acids is going to become higher. If you weaken the polarity between the hydrogen and the rest of the compound, you're going to increase in strength because it's going to be easier to break that covalent bond between the two. So strength increases with increasing polarity and decreasing bond energy. A weak acid, again, will be a weak electrolyte because it's not going to produce that many ions in solution. Aqueous solutions contain hydronium ions, anions, and dissolved acid molecules. So what's an example of this? Well, I just did it. Let's just do HF. And we add water. Let's see, that's a gas, that's a liquid. And here's a really big tell. H3O plus, AQ plus F minus, AQ. And we gotta, don't worry about balancing it. All right, so if we look at this, and then let's just do HCl as an alternative. Cl minus AQ. And let me get out the quick, because you guys, this is all still in your booklet that I put together for you. Page are we on? There should be table. Yeah. So if you look on page 449, oh, sorry, that's for bases. Oh, we'll get there in a second. 448. If you happen to have your book out or you go and watch this later, page 448 in your booklet, you see common aqueous acids in figure 1.9. You've got strong acids on the left-hand side and weak acids on the right-hand side, just to give you an idea. But here is a telltale sign. If you are taking an exam, it's asking about acids and bases and strength. I want you to look at the arrows because a weak acid is going to have double arrows. Why does it have double arrows? Because it doesn't ionize 100%. The reaction is reversible, which means you can have hydronium react with fluorine to reverse and reproduce. You've got dissolved acid molecules here and water molecules. For a strong acid, you see only a forward arrow because it only goes in one direction. It ionizes 100% and it is not reversible. Okay, that's because it's strong. It'll make more sense even when I go through the next definition of acid and base, because then you're talking about the strength of things on the left versus the right. But for now, I want you to pay attention to the arrow to determine whether or not it's a strong or weak acid, because on any exam, it should reflect that. If you have a weak acid or a weak base, it should be represented by a double arrow. And that should be the first clue. Oop. Here's another example, hydrocyanic acid. Okay, I guess I don't have the equation for that, but if we were to write it, I'll just write here on the bottom. So we have hydrocyanic acid, that's probably also a gas, plus H2O. If it is a weak acid, it's reversible. So then you get H3O plus, and you're left with cyanide. Cyanide, one of the polyatomic ions we learned last year. Okay, so in an aqueous solution, I guess I'm going to use hydrocyanic acid as the example. The ionization, which is the forward reaction, and the reverse reaction of HCN happen at the same time. So most of the solution, when equilibrium is reached, is going to be made of hydrogen cyanide and water. Hydrogen cyanide, which is this. So again, you've got that double arrow that immediately tells you that it is a weak acid because it does not ionize 100%. It doesn't ionize 100% because you have the reverse reaction happening as well. So at equilibrium, once both forward and reverse reaction rates are equal, you're going to have specific amounts of HCN, H2O, H3O, and CN. And probably we won't get to it this year, but when we talk about equilibrium, it'll make more sense as well. But we should already understand that equilibrium occurs when you have a reversible reaction. Let's go back here. When you have a reversible reaction, you're going to have equilibrium because you've got two opposite processes occurring. Eventually, those processes are going to occur at the same rate, and that is when equilibrium occurs. Strong acids are assumed to ionize completely. Okay, so it's not the same table. This is from the old version of the book. I believe it is figure 1.9 now. But these are examples of strong acids and weak acids. And look at the arrows, all one direction, all reversible. Okay, so as we keep going through the next couple of chapters, you will see the same types of strong acids over and over again. So again, look at this. We've got HCl, HBr, and HI. So those are the halogens except for HF, which I explained why. That is a weak acid, the most highly electronegative element. But HCl, HBr, and HI are all strong. Besides that, you've got sulfuric, perchloric, and nitric. So that's not really a whole lot you have to remember. Everything else is weak. Oh, sorry, push the wrong button. Why is that not going anywhere? Here we go. Big, big, big important thing. The number of hydrogens in the formula does not affect the strength. So I want you to look at the very first row, and sorry, I'm like writing all over it. You've got H2SO4, which is a strong acid, but the H2 is not the reason why it's a strong acid. But I do want you to see that H2SO4 is strong, but HSO4 is weak. This is going to come in handy, probably not today because I'm running out of time. And I don't want to rush the next two definitions. So I tell you what, oof, I don't see you tomorrow. What I will do is, what I'm going to do is I'm going to continue this topic on Thursday because I want to finish the definition part. Oh, maybe I'll do that. I'm thinking about maybe just Thursday and Friday, making this whole week. Oh no, because we don't have class on Friday. Okay. Bruh. All right. So for sure, I'm going to continue this topic on Thursday. We were not going to have bio this week, so I will have bio. Maybe I'll just make all next week bio. We'll see. But this topic is like, I'm halfway through. I've only got 10 minutes left, and I really don't want to rush the next two because they're mucho importante. Okay, I'll send a line message to make sure everybody understands what's going to happen. Okay, so anyway. Oh, my dog is barking for some reason. Okay. Anyway, so when you see the strong acid here, H2SO4, and what is produced on the other side is weak, that's going to come in a lot in the next definition, which I'll talk about on Thursday. All right, so the number of hydrogens in the formula have nothing to do with the strength, because molecules with multiple hydrogen atoms may not give them up easily, which means it's a weak acid. A great example is phosphoric acid. Hold on a second.